This is a quick video on performing static property analysis and interactive behavioral analysis of a potentially malicious file in Windows. This video is produced in conjunction with a blog post. A link to that post is available in the notes. I recommend you reference that post as there are links to the tools used and descriptions as to why we are using those tools. The goal of this video and the corresponding post is to point individuals who work in or are interested in working in incident response and want to add some level of malware analysis to their toolbox. For this demonstration, we will be using the Remnix Linux distribution developed by Lenny Zeltzer and David Westcott, along with a mostly unpatched 32-bit version of Windows 7. These two operating systems will be running on VMware 12 Pro, but this lab would just as easily work in other virtualized environments such as Oracle's VirtualBox, or you could also do this on bare metal hardware. Before we get started on analysis, let's make sure that our virtual machines are prepared. We do so by validating the configuration for the network interfaces. We want to make sure that both interfaces are on the same VMnet and that they're only able to communicate with each other. In this case, that we're going to be using VMnet 1, which is a default host-only VMnet in VMware. And we validate that same setting on Windows 7. We see that it is also on VMnet 1. We want to test the configuration or the communication between the two hosts. We do that simply by pinging the Remnix workstation from our Windows host. The Remnix workstation is configured to use 192.168.1.1, and the Windows 7 host is configured to use 192.168.1.7. It really doesn't matter what IP addressing scheme you use. This is just what I tend to use. We can see that the communication was successful. On Remnix, we will be using INetSim to simulate common web services, such as an HTTP server, DNS, and other services that we have enabled in the INetSim configuration file. To view and edit the INetSim default configuration file, we're going to use whatever text editor we prefer, and the configuration file is located at etc inetsim inetsim.conf. In the main configuration, we need to uncomment out the services that we want enabled. I have already done this on my configuration file. The default installation has a significant number of services that we want enabled commented out. I just uncomment all of the services to make sure that they're all working. We also need to make a configuration change to the service bind address, and we need to make sure that the service bind address is configured to use the 192.168.1.1 IP address, or whatever IP address you're using on VMnet 1. We also need to make a change to the DNS configuration. We can do a quick search to go down to the service DNS bind port. The DNS bind port is fine, but what we do need to change is the DNS default IP. By default, this is the IP address that the DNS service will respond with. We want to make sure that it responds with 192.168.1.1, or again, whatever IP address you're using on the VMnet 1 interface. We write our configuration, quit Vim. Now that we have INetSim configured properly, we need to start the service. So we just type in sudo INetSim, and that'll execute INetSim, and it'll tell us the services started and what PID those services are running on. We can test that INetSim is running by going over to the Windows 7 host and doing a name resolution for Google, and we can see google.com returns as 1.1, You try Cisco, we also get 1.1. The INET SIM will always return 192.168.1.1 for every DNS resolution. We can also test the HTTP server by trying to go to cisco.com, and we'll get a return of the default INET SIM HTML page. I'm not going to get into this in this video, but we can also add files and modify this HTML page hosted by INET SIM if we need to do additional levels of analysis. Like for example, let's say when we get into executing the file, that it is attempting to retrieve another executable hosted on a web server. We could provide that executable to the Windows 7 host by storing it in the INET SIM directory on Remnix. So now we've tested the environment, we know it is ready for dynamic analysis. But before we begin behavioral analysis on the file, we want to start every malware analysis process with some level of static property analysis. For this demonstration, I'm going to be using PE Studio. I have version 8.54 installed. I take the file, in this case we're going to be analyzing the file bad.exe. I drag it over to PE Studio. PE Studio will start to analyze this file for us. It takes a few minutes. It attempts to go out to VirusTotal because Windows 7 doesn't have access to the internet the way we have it currently configured. This VirusTotal search isn't going to be successful. We could always take the hash and do a search on VirusTotal ourselves, or submit the file as a whole to VirusTotal, or to ThreatGrid, or whatever automated analysis tool you use. After a little bit, the fields will stop being populated. This indicates that PE Studio has completed its processing of the file. The first page that pops up is basic information about the file. We can see its hash, its MD5, SHA-1, and imp hash. We can also see that it's for a 32-bit application. The size of the file, the entropy of the overall file, and I would recommend doing some research on entropy. It's a good mechanism to help identify whether a file is encrypted or compressed. We can also see the signature will often tell us whether the file is packed or what language the file or what compiler was used to create the binary. The next tab down we have indicators. Indicators summarizes some of the information that was discovered during processing. We can see that the file contains a significant number of blacklisted strings at 99. And we can see some other interesting symbols or functions being imported that were flagged. What we're going to do, now we can go down to the file header, and we can look at the date that this file was compiled on. This file was compiled October 26th of 2014. This timestamp is in UTC. We can go down to the imports, and we can see imports that are highlighted as blacklisted by PE Studio for us. For the sake of time, I'm not going to go through all of these imports and explain why they could be blacklisted. What I would recommend doing is going through each of these functions, and you can right-click and do a query MSDN. Since Windows 7 isn't online, it can't go to MSDN and do that query for us. But you can go to MSDN and do a search for that function import on your own, read about it, and in the case of is debugger present could be used for anti-debugging purposes. It can identify whether a debugger is being used on the host, and then perform additional actions. If we were going to be debugging this application, which we're not, we would have to deal with that probably by adding a null operation to where that function call is, or modify the return value, or do some other things to try to avoid it. Right. We can also go look at the strings. Typically what I would do is export the strings out to a CSV file, and then do greps against the strings to try to find any web address calls or IP addresses that are stored in strings. Those types of things we should be able to identify. We can use this information now from static property analysis to make sure that our lab environment is set up properly for execution of this file. We know from the file header that this is a file that is intended to be executed on a 32-bit processor. We saw that summary again up top, where it's for a 32-bit operating system. If this malware needed to be executed on a 64-bit system, we would also want to have a Windows 7 or some version of Windows that's 64-bit available. If during our analysis we see that during our static property analysis we see that the file is likely to call a vulnerable version of some specific application, we would want to make sure that our Windows environment is set up with that vulnerable application so the malware would execute properly. We would want to take notes on everything that we've seen here, on our assumptions. Keep a notepad on your host running. Take screenshots of things that you think are interesting. Do searches on the hashes. Look up other people's analysis on these files. There's a significant number of things you can do with static property analysis before actually executing the malware to make sure that everything is set up right. You may not even need to do behavioral analysis if you don't want to. You may be able to find somebody else's analysis. So now that we've completed property analysis using PE Studio, we're going to start prepping the environment to behaviorally analyze the file. First thing I'm going to do is I'm going to start Process Explorer. This is a sysinternals tool used, which is essentially a more powerful task manager. We can see all the processes running and the resources they're using. If we wanted to see more details about a process, I could say go to Explorer and go to Properties, and I could look up different information about the process as it's executing in memory. I can also find where it's what current directory it's executed from, where its path is. It's a very powerful tool. It even has a submit to virus total option built right into Process Explorer. We're going to be using Wireshark and Process Monitor to actually monitor the execution of the file. I'm going to start Wireshark first. I'm just going to move it over to the side here. And then I'm going to start Process Monitor. Before I start the capture on Process Monitor, I'm going to start the capture on Wireshark. And then I'm going to start the capture on Process Monitor by hitting OK. Process Monitor is going to capture all changes to the operating system and file system that occur, and Wireshark is going to capture all the network communication that occurs. Now we're going to execute the sample as administrator. I'm going to snap Wireshark over to the left here. While it's executing, we can filter for DNS so we can see DNS resolutions occur. And in Process Explorer over here, we can see additional processes and child process is executing after we've executed our potentially malicious sample. Pretty soon here, we'll start seeing domain name resolution requests. We can see just as they're scrolling by, we can see there's .rus being called. The only thing that we've executed is that malicious sample, so it's reasonable to assume that this activity is related to that sample executing. After a period of time, the samples will usually enter a sort of idle state, or a state in which they're continuously repeating the same activity over and over again. By monitoring the Process Explorer and the activity in Wireshark, we can get to a point where we're comfortable stopping the execution of the malicious process. Once we feel comfortable that the process has completed its primary goal, we want to kill the process tree from the parent process, the parent malicious process. We allow it to exit, and then we stop the Wireshark capture, and we stop the process monitor capture. Now we need to export the data from process monitor so that we can use it in another tool here in a second. Before we do, we want to make sure that we go to options and select columns, and we make sure that this thread ID column is being displayed. We go to File, Save. We want to save all events, and we want to save it as a comma-separated value. And we're going to save that to the desktop. In this case, I'm going to leave the file named as log file. You may want to change that name to a date timestamp, or change it to some other descriptive name. I hit OK. Give it a second. It exports the log file CSV. We're going to want to do something similar here with Wireshark. Go to File, Save As. I want to make sure to select Wireshark/TCP dump. This is the legacy format, PCAP format. I'm going to save that to the desktop as well. And I always name the Wireshark packet capture the same name as the CSV. So that way, when I'm moving these files around, I know that they're associated with each other. And I export that. So we have the log file PCAP and the log file CSV on our desktops. You can open this CSV file in Excel or in a notepad editor because it's simply a comma-separated value. Process Monitor maintains a timeline of all actions that occur on the host while the capture is occurring. We can use grep and other tools to help parse out this timeline and identify items we need when we're writing a report and we want to get down to the specific timestamp that a process executed or the length of time between events occurring. This tool is looking at this data in CSV format is very useful. We can also take this information and we can graph it. We're going to use a tool called procdot to graph the malware execution. Procdot can take as an import the process monitor CSV file. It can also take the PCAP data as an import as well. I'm not going to be importing the PCAP because it will it's not going to graph very cleanly for this demonstration. So we'll stick to the process monitor CSV file. I'll go and select that from the desktop. After I click the ellipses next to the process monitor, it opens up this dialog. We click log file CSV, open it. Launcher will, from Launcher we can select the process that we want graphed. It's going to analyze the procmon file. We want to graph the bad.exe process to start with. Eventually we will, you could go in and graph the other sub-processes. We double click bad.exe. I'm going to select compressed from these checkboxes. Help minimize the amount of information that is being graphed to make it more readable. Compressed will reduce the number of registry keys that are being displayed. Click refresh after I've selected that. Now we can see a detailed graph of our process executing. Before we zoom in, I'm going to export the graph into a PNG file that can be used in a report later. Save it to my desktop. I'll name it bad.png. And later, when I'm writing my report, I can use this as an artifact of that report. I can zoom in and see that bad.exe executed as PID 4004. It created a file in the temp directory with this long, seemingly random name, .exe. Then it loaded that file and created a process as a child called at PID 1408. This child process created a number of files to include one in the Windows directory named jveg and so on .exe, and created a process based on that file that it dropped. We can click on, this graph is interactive, and we can click on the process, and we can right click and go to details, and we can see details about this process execution. We can see that it has 2 threads that were executed within that process. We can see the full path and the command line used to execute it. Next steps in analysis would be going to these file locations and comparing the hashes of these files in Windows and the files in temp, and validating whether they're the same hash as the originating file or new hashes, and might indicate that the file was that the file was dropped from the parent, or is an exact copy of the parent. Some malware will store within itself, in its data section or resource section, a compressed additional file. Since we're not allowing this to talk out to the internet, we know that this file isn't downloaded, that this file has to be present in the originating malware. Here we see PID 2316, which was executed from the Windows directory, was the process making HTTP callouts. Again, here we only see 192.168.1.1. That's because this virtual machine is not allowed to communicate out to the internet. If we did allow it to communicate out to the internet, we would see other IP addresses here. We also see some additional files that were created from PID 2316. It created yeah, it created some additional files in the Windows directory that we would want to go to and analyze those files as well. And we see that the temp file was deleted here, right? We can use this information that we gained during the static property analysis to write YAR rules that can be used as signatures for scanning hosts throughout the network. The behavioral analysis data that we collected from Process Monitor can be used to write OpenIOCs. We see that it created a number of files. It also modified some registry settings too, and we could have expanded those registry settings out and added those to OpenIOCs. The network communication that we identified in in Wireshark, in the PCAP data, we could use to write snort rules. Using this information, we discovered we can properly scope our incident, finding additional hosts which could have been compromised as well. Thank you for your time. If you use different tools or you want to comment, feel free to do so below or in response to my blog. You can also contact me on Twitter @obsec, and you can find my blog on Medium @obsec as well.